So good morning to everybody. I hope that everybody is well and recovered well after the Diwali dinner. So we are starting today's session by a talk of Anupam Kundu, who I think is just joined the ICTS very recently. And Anupam is going to tell us about exact gap statistics in the wrap model on a ring with a tracer. Thank you, Anupam.
Uh, I'll present some exact results about gap statistics for the random average process on a ring where you have a tracer particle which could be driven or not driven. So this work is done in collaboration with Julia Cividini, who is a postdoc at Weizmann Institute of Science, and David Mukammel. He is also from Weizmann Institute of Science. He was here in the first week of this conference, and Satya Majumdar, whom you heard yesterday. So this is the reference of this work. So interacting many particle systems have been studied as examples of many body systems in equilibrium physics, and there are well-defined procedures to study these kind of systems. But in non-equilibrium physics, interacting many particle systems, there are a few model systems which have been studied and in detail. And among them, the most studied example is the exclusion process, as you all know. And this process usually in one dimension is defined on one-dimensional lattice, where particles move from one side to another, one side to the neighboring site, and particle moves to this neighboring site on the left or on the right with specified rates, and this move becomes successful only if the target site is empty. And for this model, many things are known, for example, density fluctuations, current fluctuations, correlations, many stationary properties and non-stationary properties are known, and these results have been obtained using sophisticated techniques. So there is another interesting many particle system which is also widely known as random average process. This name was first introduced by Ferrari and Fonitz in 1998, and this is also known as RAP in short. In contrast to the exclusion process, this process is defined on a continuous line, where particles move on this continuous line, and it also any particle also moves in the right or in the left with specified rates. But when it moves in a specific direction, it moves by a random fraction of the space available till the next particle in that direction. And this random fraction is chosen from some jump distribution r eta. So for example, in this picture we have a ith particle whose position is xit, and if it moves in the right direction, it moves by this fraction of this space available with this probability, and if it moves in the left direction, then it moves by a random fraction of the space available till the next particle on the left direction, which is this much, with this probability, and it doesn't move with probability 1 minus dt. So that gives you the position of this particle at time t plus dt, where dt is a small time interval. So this defines the dynamics of the particles. So that's how we define the process, that this is the random average process, and this process appears in various physical situations, like in traffic model, in wealth distribution model, force fluctuation in granular media, etc. In this talk, I'll be interested in random average process defined on a ring. Our particles move on this continuous ring in presence of a special particle which moves differently than other particles. All other particles move to the right or to the left with equal rate, which is half. But this particle moves to the right or to the left with different rates. Here this particle moves to the right with rate p and moves to the left with rate q. And for this system, we are interested in the gaps between successive particles. More precisely, we are interested in the joint distribution of the gaps in the steady state, this quantity, for given size of the ring L and the number of particles n. In particular, we would like to focus on two cases. One is p equal to q case, where all the particles are moving symmetrically. Here I would like to emphasize that p equal to q does not mean that p has to be equal to half, but still if p equal to q, all the particles are moving symmetrically. And the other case is p not equal to q. That means this particle is moving asymmetrically, which is driven. This particle is driven. So we like to find out this quantity, study this quantity for these two cases. So since we are interested in the gaps, so it will be convenient to map this problem into a equivalent mass transfer model. And how does this mapping work? So this mapping is done as follows. Corresponding to n particles in this RAP picture, we consider a periodic lattice of n sites with some masses on each site. Now each particle in this picture gets mapped to a link between two successive sites in this mass transfer picture. For example, the ith particle in the RAP picture gets mapped to a link between sites I and I minus 1 sites in empty picture, sites. So as a result, this particular stressor particle will get mapped to a special link which is between n and 1. And mass at each site in this picture will be related to the gap between successive particles in this picture. So mass at site I is equal to the gap between the particles, ith particle and I plus 1th particles in the wrap. So as a result, for each configuration of the positions of the particles here, there is a unique configuration of the masses in this picture. However, the converse is not true, because by doing this transformation, we lose a global translation degrees of freedom. So we see that the gaps in this picture are basically masses in this picture. So I'll be using these two words, gaps or mass, interchangeably from now on. So once we have made this mapping from this picture to this picture, so it will be good to write down the dynamics in terms of the masses itself. And starting from the dynamics of the particles here, you can write down the dynamics of the masses in this picture, and you can write down the dynamics for each, which can be written for each bond. For example, dynamics at I and I plus 1th bond. And in this bond, there are two processes. One process is that some amount of mass from site I goes to the site I plus 1, and some amount of mass from I plus 1th site comes to site I. And these two processes happen with these probabilities. Now if you consider processes in this special link, then these two probabilities has to be changed accordingly, which you will be able to figure out quite easily. So now, as I said, we are interested in the distribution, joint distribution of the gaps in the steady state. So we should look at the steady state, and we should start from the steady state master equation given this dynamics. And the steady state master equation can be written by equating the total outgoing current is equal to the total incoming current. So this is the total outgoing current from a configuration G, which is like this, and this is the total incoming current to this configuration from each of the bonds. This is similar to this, except that at site I and I plus 1, the masses are different from this. And you can see that whenever this bond, whenever this particular, you consider transitions involving this bond, then the rates will be changed accordingly. So in simple words, we would like to solve this equation for this quantity. This is the joint distribution of the gaps in the steady state for given L, which is the size of the ring in the RAP picture. Now it is the total amount of mass in this mass transfer picture and the number of particles. So let us start with this symmetric case when this particle is moving symmetrically, that is P is equal to Q. And let us start for this case. And for you know that for different choices of jump distributions r eta, with which the particle jumps to the in one direction to the next particle, this joint distribution in general be different. And finding such a joint distribution for arbitrary r eta is a rather difficult task. So let us consider the following relatively simpler question. Is it possible to have joint distribution in the factorized form, in this following factorized form, where this delta function represents the total mass conservation? And if the answer to this question is yes, that is, if it is possible to find the joint distribution in this factorized form, the question is for what choices of jump distribution one should be able to find this joint distribution in this factorized form. So to answer this question, what we do, we start from this form, this factorized form, and insert that in the master equation. And we see that the master equation will be satisfied in this by this factorized form only if we choose. One can also solve, one will be able to get an equation from which you get the solution if we choose that the weight factors here are given by this form, where a naught and b naught are constants, they do not depend on g, and beta is a parameter which is given in terms of the moments of this jump distribution, where mu1 is the first moment and mu2 is the second moment. And corresponding to these weight factors, we find that the jump distribution has to satisfy this this integral equation for any u greater than or equal to 0. Now you see that this distribution, this weight factors does not depend on I. So that means this is same for each sides. It's a kind of homogeneous weight factors, which is also true because for p equal to q case you will see that it will be homogeneous. And if you take these weight factors and put it here and absorbing this constant into the normalizing constant, then the joint distribution looks like this simple form where the weight factors are simply given by this power laws, and the normalization can be computed easily, and which is given by this, where n is the number of particles and L is the size of the ring. Now let us consider the second question. For what choices of this jump distribution one has the joint distribution in this factorized form? So we saw that R eta has to satisfy this equation for any u greater than or equal to 0. The question is, what are the solutions of this equation? So there are infinitely many solutions of this equation for R eta, and we would like to classify them according to the values of beta here, this parameter here. However, I would like to mention that this classification which I am going to tell you is not complete. This characterization is not complete because it does not include all the possible solutions. However, it provides some solutions. So let us start with beta equal to 0 case. So at beta equal to 0, the solution is this delta function. This is not a very interesting solution because for this case the dynamics goes to an observing state where all the masses pile up at one site, and this is a kind of trivial case of condensation. Beta equal to 1 is a very interesting case because in this case all the possible configurations appear with equal probability, because if you see that if you put beta equal to 1, this factor becomes 1, and so it's a flat distribution of all the possible configurations. And for this case you can find out, these are some examples of the solutions, like this is a beta kind of solution and this is another delta function. In fact, for beta equal to 1, you can find out all the possible solutions in terms of this function, where f eta is a real positive function and this is symmetric around half and it satisfies this condition. You can check that with these conditions, one can check that this will satisfy this equation with for beta equal to 1, and it also gives beta equal to 1 if you compute this. So for beta equal to 1 you can find out all the possible solutions. Let us look at other betas. So for general beta we have found one class of solution which spans the full range of beta, and this is given by this kind of power law behavior. And note that beta equal to half corresponds to this uniform distribution, uniform jump distribution. Another interesting case is large beta case, because in this case the jump distribution can be expressed in terms of this scaling form, where phi y is a real and positive function, and it satisfies this relation that the Laplace transform of this function evaluated at 1 plus u and Laplace transform of this same function evaluated at 1 over 1 plus u is equal to 2 for u greater than equal to 0. And you see that for at phi hat at 1 is equal to 1. In fact, this equation also has many solutions, and one class of solutions can be written in this rational form, where HUS and HBS are polynomials of same order, say m. So there are two m plus 2 constants associated to the coefficients of different powers of s, which one has to specify, but among them only m plus 1 are independent because of this relation, and the other rest of the m plus 1 constant has to be chosen so that this phi hat at 1 is equal to 1 and the inverse Laplace transform of this function becomes real and positive. And the simplest example is this is 2 over s plus 1. You can check that this satisfies this, and the inverse Laplace transform gives this exponential distribution. But there are other explicit solutions of this you can try to figure out. So as I said that there are many solutions of this equation for r eta, but this classification which I presented is not the complete one. It does not characterize all the possible solutions of this equation. However, let me make some general remarks about the solutions of this equation. So if r1 eta and r2 eta are solutions of this equation corresponding to same beta, then if you construct this linear combination of these two solutions where small r is within 0 and 1, then this is also a solution of this equation. And the second remark is that if r1 eta is a solution, then if you construct another solution where again small r is within 0 and 1, then this is also a solution, and this just implies that you are rescaling the rate factors by 1 minus r. As a result, you are basically dilating the time by factor 1 over 1 minus r. So we see that there are many solutions, and corresponding to these solutions we have this joint distribution in this factorized form where the weight factors are given by this power law behaviors. Now there are some universal properties of this joint distribution, and these are as follows: that this distribution does not depend on the explicit forms of the jump distribution which have same beta and also satisfy this condition. Second, you see that this equation does not depend on the jumping rate of the tracer particle, so it does not depend on p as long as p is positive. It does not depend on p. And even when the individual particles have their own rates in this form, such that the rate at which they move to the right minus the rate at which they move to the left is a constant which does not depend on the sides, then also you can show that the joint distribution will be in this form. So this, why does this universal feature appear, we do not understand completely, but in some sense this is quite similar to the equilibrium situation where you can change the rates still maintaining the detail balance. However, the invariant distribution in the stationary state is independent of the rates in the equilibrium, so which is quite similar to this. However, this distribution does not satisfy detail balance, so this is not an equilibrium distribution in this case. Okay, so we have this joint distribution of the gaps for a ring of size L and number of particles n. So let us look at the single side mass distribution. And the single side mass distribution can be obtained by integrating out all the gaps except one, and you can do this integration, you find that this will be given by this beta distribution, and which in the thermodynamic limit, taking n going to infinity and L going to infinity, keeping the gap density fixed, you will see that this distribution can be written in this form, this gamma distribution. So these kind of distributions have been studied in various other models like conserved mass models by Rajesh and Satya, then in asymmetric random average process with different other dynamics, parallel dynamics or random sequential dynamics, this kind of distribution, even the joint distribution have been studied in this context. So let us now compare our numerical results for this single side mass distribution. So we computed single side mass distribution numerically for different choices of jump distribution. This jump distribution satisfy this relation. So we should expect that the numerical distribution should match with this result, which they do. because here the points are from the numerical calculation and the solid lines are theoretical curves. And the betas corresponding to these distributions are given here. Interestingly, sorry? Others are moving with half, and this is P and P. That's the rate. Interestingly, you see that there are some distribution like the jump distribution like this one. This does not satisfy this equation. But still, if you then compute the numerical at the single site mass distribution, it still is very close to this single site theoretical distribution. So the question is why? So this happens because in the thermodynamic limit, the joint distribution is in fact in the leading order is a product form, where this function is basically, one can show that this function is given by this gamma distribution, and in the next order, which is at order 1, you see deviations from this factorized form, which comes from the correlations between gaps at different sites. So we have computed this correlation also for arbitrary eta, arbitrary jump distribution, and you can see, one can show that this correlation is given by this explicit form. However, in the larger limit, you can see that the on-site fluctuations are given by this, which is order 1, whereas the correlations of diagonal correlations are order 1 over n, and this you can also obtain from this distribution, so it's consistent. So till now we have studied the P equal to Q case, where we studied the joint distribution, single site mass distribution, and found out that there are some choices of R eta for which you can find out this factorized form, and we studied the correlations. So let us look at what are these results for the P not equal to Q case, where this particle is driven, is moving asymmetrically. So in this case also, in the thermodynamic limit, the distribution is in the factorized form in the leading order, and there will be order 1 over n corrections which arises because of the correlations. However, note that now these factors depend on site I. They are not homogeneous. This is because of the drive, the density, gap density, and the fluctuations will now become homogeneous. They will start depend on positions. And one can also find out this distribution, and this distribution has the same gamma form, except that this quantity now depends on I, which was independent of I in the P equal to Q case, which is the average gap. Now it depends on I. Now the question is, how does it depend on I? To find out that, once again we start from the master equation, and we see that this quantity satisfies this recursion relation. This is a simple second order difference equation with boundary conditions, and which you can solve easily, which has a linear solution. And if you put P equal to Q, you see that this is equal to omega naught. In fact, in the large n limit, this has this scaling form. The scaling function is this linear linear function with a discontinuity at the position of the tracer. So it's basically, this is on a ring, so it basically goes like this, and there is this discontinuity. So now, once we have this I dependence, so let us try to compare our numerical results with the single site mass distributions. So we computed single site mass distributions at 4 different sites, 1, 33, 97, 128 for a system of size 128, and for 2 different choices of R eta. So squares are for R eta equal to 6 eta times 1 minus eta, and circles are for uniform. And we see, and we compare that with this theoretical formula. We see that as when we are far from the tracer site, this distribution matches quite well with this function. Exactly at the tracer site, there are some discrepancies because the effect of the drive is strongest at the position of the drive. And we believe that if you go to larger system sizes, it will become better. So we see that in thermodynamic limit, we have that in the leading order, the distribution is factorized and it is inhomogeneous. And in the order 1 over n, there are correlations. There are deviations from this factorization form, and which arises because of the correlations. So let's look at the correlations in this case also, the 2-point correlations. So to study this 2-point correlation, once again we start from the master equation and write down the equations for this 2-point correlation, which is given by this, which satisfies this equation. And by definition you see that this quantity is symmetric, and because of the mass conservation this quantity satisfies this kind of integral condition. And this equation has a simple structure. You see that on the left hand side this is a discrete Laplacian, and these terms lie on the diagonal, and the line above the diagonal and the line below the diagonal. So now we want to solve this equation. So before going to solving this equation, let us look at the numerical results. So we numerically computed this dij for different values of n, and we plotted dij times n times the particle density square as a function of the scaling variable for 3 fixed values of j. And we see that the data for different n collapse, match, fall on top of each other. We do the same for the diagonal correlation for the fluctuations. This is for off diagonal, that is I not equal to j. We do it for diagonal correlation also. So we compute this quantity for different values of n, and then we plot this quantity multiplied by density square as a function of this scaling variable. And we see that again here the data for different n match on fall on top of each other. Note that in this case we have multiplied by n, however here we did not. So this suggests that these quantities, as in the p equal to q case, off diagonal correlations are order 1 over n and the diagonals are order 1. On top of that, this overlap implies that these quantities have this kind of scaling forms. Here I have also included the next order correction to this order 1 scaling form. So now what we do, we want to find the solutions of these equations in this forms. So for that what we do, we insert these forms in this equation and take the n going to infinity limit. As a result we will reach a continuum limit of this equation, and we get this continuous equation. So this equation we get at from order 1 over n, and then we get information about these two scaling functions at order 1 over n square, and at order 1 over n cube we get this differential equation. You see that there is this Laplacian which comes from this discrete Laplacian, and these terms which lie on these 3 lines. So when you take n going to infinite limit, all these 3 lines merge to this diagonal line, and you use these relations and then you simplify, it provides a source to this differential equation. Now since the tracer is driven, so there will be some boundary conditions, and these boundary conditions comes from the equations at the boundaries, and from these boundaries you can find out this boundary condition. You see that this here the function is discontinuous and the derivatives are continuous, and this integral condition now looks like this. So this equation is defined on this unit square with this boundary condition which we have to solve. So for solving this equation, you note that this equation can be thought of as a Poisson equation, where this is a kind of electrostatic potential and this is a charge distribution along the diagonal. So to solve this equation, what we do, we start from the Green's function. So but this Green's function cannot provide the solution of this equation, because you see that this charge distribution has a net 0 charge. If you integrate on this square, this will also give 1, this will also give 1, it has net charge 0. So this equation this Green's function cannot give the solution of this equation. So what we have to do, we have to modify this equation. So we have to add a suitable charge distribution so that on the right hand side the net charge becomes 0. So we add a suitable charge distribution and then solve this equation with this boundary condition. And once we have this solution, then one can write down the solution of this equation in this form. This is the particular solution and this is the homogeneous solution, where the constant in the homogeneous solution can be determined from this equation, this relation. Now we have to solve this equation for any p and q, and to solve this, before that note that this Laplacian operator with this boundary condition becomes non-self adjoint. So to solve this equation, one has to be a little bit careful. So what do? You choose the basis function in such a in careful way and expand the delta function in that basis function and the solutions also, and then you do the solutions. And one can find out the solution for any p and q. Here I am presenting the solution for q equal to 0 case, and the solution is given by this expression, which looks long, but it's quite simple. So once we have this Green's function, if you use that, you get this full scaling function of this quantity for I not equal to j, and we plot them, we compare that scaling function with the numerical data, and we see that they are matching pretty well. The same thing happens for the diagonal correlation also. So in the diagonal case also, if we this line corresponds to this expression, so this one, it also matches quite well. And the information at the next order, which satisfy this function, satisfy this relation, which we also verify numerically and theoretically here. Okay, so we have studied gap statistics in the steady state of random average process defined on a ring with special particle which moves differently than other particles, which could be driven or not driven. So in the symmetric case, we find that there are some choices of jump distribution for which this distribution has a factorized form in this form, and this distribution has some universal features also. And in the other case, for p not equal to q case, we find that this distribution in the leading order is a factorized form, and then there are deviations from this factorized form which can be quantified from the correlations. And we looked at the 2-point correlations in this case for the p not equal to q case, and we find that these correlations have this kind of scaling forms, and we found these scaling functions exactly. So there are a few further future directions of this problem, of this work. So as I said, this the solutions, this equation has many solutions, in fact infinitely many solutions, and there are the complete characterization of all the possible solutions would be very nice. Then one can try to study the center of mass of this problem in the RIP problem. In the p equal to q case, one can show that the center of mass diffuses, and the diffusion constant is given by this factor. Whereas for p not equal to q case, it's not clear what does the center of mass do. From the numerical simulations, it looks like that they also diffuse, but the diffusion constant does not match. So how do you find out this diffusion constant? So in a small time interval, you can show that the change in the position of the center of mass can be written as a sum of the masses in the mass transfer problem multiplied by some independent random variables, which looks like this. So delta x is 1 over n. And these are psi i's are independent of gi's. And now in the large T limit, you can think of that the gi's have reached the steady state, so you can use the factorized form in the leading order in the thermodynamic limit, and you can try to find out the variance of this quantity using the statistics of gi's, and from there you can find out the diffusion constant. Now if you do the same procedure for the p not equal to q case, and you can get a diffusion constant, but it doesn't match with the numerics. There is a finite factor for q equal to 0 case, it's 2, and for p and not for p given p and q, it depends on with some function, the factor depends on this p and q. So it's not clear what will be this motion, but it seems that the 2-time correlation of these gaps becomes independent, so becomes important. These 2-time correlations individually are not important, but in the calculation you find that there will be some of this correlation will come, and that may give some extra contribution, so which is not very clear at this moment. And one can also look at this problem on the infinite line, which will be also interesting, and to look at the fluctuation, the variance of the tracer particle, even the correlations, two tag correlations of this problem in the large T limit. So thank you for your attention.
Thank you very much. We have quite a lot of time for questions. Are there any questions? Gregory?
I would like. I would have two questions. Actually, the first one is the following. So you considered this steady state solution which have this factorized form. Now, natural question would be: would it be possible to construct pair factorized states? I mean, as it was done in this context of mass transport by Evans and Satya.
Yeah, in that case, I think the rates has to be changed. It should involve the masses at two different sites, and one has to change the rates, which will involve the masses at two different sites. I think in that case, I think one can try to do that also in this case.
The other questions that I had is concerning in the P different, I mean, from Q case, where you showed these correlations, Dij. Now they clearly have a sort of non-analytic behavior. I guess mathematically this is due to the boundary conditions, I suppose, but physically what does it correspond to? I mean, is there any meaning to that?
Which portion you're talking about?
Yeah, I mean,
Oh, this point is, so this is because this point is not in this. This is x equal to I equal to j case. So for at I equal to j, the fluctuations are order 1, whereas the correlation when I and I plus 1 is of order 1 over n. So this function goes somewhere, whereas the fluctuation is there. So this is like this. This is the usual which happens in the correlation function. But these things, these discontinuities here, this discontinuity appears because of the tracer.
because the asymmetry of the tracer. Okay.
Yeah, because of the asymmetry of the tracer.
Okay, thank you.
Could you go to the next slide? I'm a little confused about the matching. So the tracer is at 0, yeah?
The tracer is at 0.
Which is the same as 1.
Actually, in 1 over n going to infinity limit, it's actually 0, and this is a periodic, so it's same as 1.
Yeah, so I'm confused
There is this
as to
discontinuity.
what is breaking the symmetry. I mean, it seems to match very well on the left, but not
No, this you have to go to very large n to match this.
But why is it matching very well on the? I mean, what is breaking the symmetry? I mean, it should match. It should. I mean, I would have thought it's either matching on both sides or not matching on both sides.
See, if the tracer is moving this way, suppose predominantly, so the fluctuations in this direction is less because the gaps will be very small because it tries to move all the particles. Whereas in the back, these particles are not feeling this one less, feeling this particle less, presence of this particle less. So the fluctuations are larger at the back. So this is at the back, and this is in the front.
Oh, so P not, when you say P not equal to Q, you are saying P greater than.
Yeah, this figure corresponds to P greater than Q.
Okay. So that is what is called.
Yeah, this figure corresponds to P greater than Q.